It's a pleasure to have Danny Ruberman here. He's going to tell us about diffeomorphism groups and embedding spaces for four manifolds.
So, thank you. It's always a pleasure to be visiting the department here, visiting Miami. So I will tell you, I'm a big fan of the ocean, so he took me to the beach over the weekend. So it's been a great visit. That's about it. What's that? Yeah, it's about 20 degrees cold. Anyway, well, okay. So as the title says, I'm going to talk about diffeomorphism groups of four manifolds and some things about embedding submanifolds in four manifolds. And this is all a joint work with Dave Auckly. It's kind of a long-term project. I don't remember the conversation, but Dave says we discussed this in 1998. So, I mean, I know, I recognize that we might have, but we certainly had talked about it all over the years. So anyway, so the theme is, it's several sorts of interactions between constructions and detections of interesting diffeomorphisms of four manifolds, and the way that that uses embedded surfaces and says things about embedded three manifolds. Okay, so let me just sort of back up with start with a little prelude, which sort of captures, at least is an important part of the setup here, and I'll actually use some of these things. So Donaldson showed us a long time ago, 1984, that you can have Donaldson, and I should also the work of Freedman for the homeomorphism part showed that there were four manifolds that were homeomorphic but not diffeomorphic. So that's quite striking, contrary to what one might expect from high-dimensional topology. Here's a concrete example which I'll make some use of, although actually I realized the way I set up recycled a few slides. So this probably isn't exactly the right example, but anyway, for what I'm going to use later, I would have to use more elaborate things. But anyway, this is a one that one can think about. In CP3, you can take the hypersurface defined by a polynomial, make sure that it's generic, so it's a smooth hypersurface. Take the one of degree 4. That's the famous, that's a K3 surface for elliptic surface. And among elliptic surfaces, that would be the elliptic surface E2. Some homomorphic invariant. And then if you take that and blow it up once, so that would be a blown up K3 or blown up E2, then Freedman tells us that up to homeomorphism. So just so you get the notation, this little squiggly double squiggles, that means homeomorphism. That's homeomorphic to a much simpler manifold where you add 3 copies of CP2 with its standard complex orientation and 20 copies of CP2 with its opposite orientation. So those are homeomorphic manifolds, but Donaldson showed that they're not diffeomorphic. Quite striking. Both sides of that are so this symbol, well, without the slash through it, that's supposed to be diffeomorphism. Okay, and he did this by introducing what one might call, what everybody else called Donaldson invariance, and so he invented a certain invariant. In this case, it could actually just be a number and an integer. And some 10 years later, there were the Seiberg-Witten invariants introduced by Seiberg-Witten, which sort of reformulated things. And so those are also numerical invariants, but those are a function on spin C structures, or as just if that's not a meaningful phrase, you can think of it, in this case, it's a function on the second cohomology. So Freedman, as I say, would say that those manifolds are homeomorphic. That's a hard theorem. So one might say that that's an exotic pair. So exotic generally means things that are topologically the same but smoothly different. So well before any of this, and actually related sort of as they used in Freedman's work, is the fact that if you have any two manifolds that are just simply connected four manifolds that are just homotopy equivalent, so even weaker than homeomorphic, then then they become diffeomorphic after you add enough copies of S2 cross S2. So add means connected sum, so you move a ball and put them together. And so that's a very striking result. That's an old result. I enjoy looking around the room and seeing who was alive at the time that was born. You don't have to raise your hand if you weren't. I think. Yeah. Anyway, yeah. So
in 10th grade.
Yeah. Okay. Well. Okay. So you might have read that paper.
Yeah.
But you know the result's very general. Actually, it's not so hard that result. But in the 70s, people started to say, well, how many Ks did you actually need? And so there's some fabulous results of Moishazan followed by Mandelbaum and then works together, where they showed that you can often just take one such thing. So this adding S2 cross S2 or adding some simple manifold is generally known in the trade as stabilization. So a small point which you might wonder about, well, as we get to the bottom of the slide, connected sum is really an operation on oriented manifolds. So it actually matters whether you add, for instance, CP2, which for lots of examples like this one, this one, those manifolds, if you add CP2, become diffeomorphic. If you add CP2 bar, in other words, as in blowing up, then that doesn't actually change anything. So there's a big dip. So there's some orientation so one has to be careful about orientations. And, anyway, Mandelbaum and Moishazan show that for that particular example, you could just take K equals 1. And in fact, it's an observed phenomenon that for all the examples that anybody's ever cooked up of exotic pairs of closed four manifolds, they become diffeomorphic after adding just one copy of S2 cross S2. Very striking, and that's a conjecture. It sometimes goes under the name of one is enough. It's not true if you have manifolds with boundary. That's a striking result, a recent result of Kang. And as I say, if you add CP2 bar, nothing happens. Well, they remain. That preserves these distinctions. That's a consequence of work of Donaldson. So I want to concentrate on. So let me call just for the notation. X is a complex surface, the blown up K3 surface or E2, and Y is its sort of simpler topological model. Okay, and those are so X and Y will sort of be that. Or something like that for the remainder of the talk. And well, so the thing I want to point out, of course, is so let me give the thing that they're both diffeomorphic to. I'll just call that Z. Okay, so in other words, you want to think of really this one manifold Z with two different decompositions. So I could break it up in two different ways where the pieces aren't the same. So this is, of course, different from what happens in dimension 3. Where there's a unique decomposition into different pieces. Okay, so the principle at least says that if you keep track of, that there's some things about Z, if you sort of allow yourself to keep track of some extra information. So, for instance, I'll explain one of them first, and then a more complicated one after. You can kind of keep track of whether you're talking about X or Y. So let me try and make that more concrete in a couple of different ways. So, well, okay, so inside S2 cross S2, of course, that's a product of spheres, and you have two spheres. The first one and the second one. So the A and B for the first sphere, the second in that product composition. And if you think of our Z as, say, X, connect some S2 cross S2 and take the first of the S2s, that gives you a sphere, which I'll call SX. So that's the A sphere from SX. And similarly, there's another one that's the one coming from the decomposition as Y connects on S cross S2 cross S2. Those two spheres are not the same. They're not. There's no way to move. You can't move one to the other by a diffeomorphism. Particularly, they're not isotopic. You could arrange that they're homotopic, and in fact, you could arrange that there was a homotopy through homeomorphisms. In other words, they're topologically isotopic. But they're not the same because if you, whenever you have a sphere with self-intersection 0, with trivial normal bundle like this, you can do a surgery, which means you remove the sphere across D2, that's the trivial normal bundle, glue in D3 cross S1. If you do that to the one coming from X, the decomposition involving X, you get back to X. If you do the one with the decomposition coming from Y, you get back to Y. So those spheres can't be the same. So in other words, that extra data, if you like, the pair of Z comma Sx is different from the pair of Z comma Sy. Okay, so that's sort of, there's nothing, I mean, that's interesting, but maybe not that remarkable, but I think that's interesting. There is, as I say, a homeomorphism. In fact, you get that homeomorphism by an ambient isotopy that just drags the one thing to the other. Or you could do that with the other sphere. You could do it with the B sphere as well. Okay, so in that sense, those spheres, the first of those spheres, the X and the Y, one coming from X and Y, those are sort of an exotic pair of submanifolds, exotic pair of spheres. And okay, so another thing which I'm going to sort of say less about, generally speaking, which is that so this is sort of a picture of, well, here I guess this is supposed to be, this is a picture of Z decomposed as X connects some S cross S2. And in fact, well, when you do a connected sum, of course, there's a 3-sphere that separates the two pieces, and so you could sort of say that the 3-sphere that separates the one decomposition is is not isotopic to the 3-sphere from the other decomposition. So those are an exotic pair of 3 spheres. Okay, so far so good. All right, and again, those sort of so here's a, you could say this. I mean, here's a fancy way of saying something, I think, very simple, which I just outlined about. So you can think of these as saying something about path components of embeddings, basic embeddings. So, okay, why would I bother? Because a few slides down the line, I'm going to say something about other homotopy groups of these spaces. Okay, so that's just about submanifolds, but there's a more subtle thing, I think, which is a variation of something that I discovered, which maybe I'll refer to. So again, way back when in 1998, which is with that 2-sphere you can do, or with those two 2-spheres, you can do something interesting. So S2 cross S2 has an interesting diffeomorphism. Well, maybe it's not interesting. Anyway, it has a diffeomorphism where you take just each 2-sphere and just reflect it. So that's of course on each 2-sphere, it reverses orientation. It acts by -1 on the second homology. But if you do that in sort of the A direction and then sort of do it in the B direction, then it preserves the orientation, because as we all know, too long would make a right. So, but it still acts non-trivially on homology. It acts by -1 on the second homology. There's other descriptions about that for that, but anyway, that's a good one. And since it preserves the orientation, well, it fixes points, but in fact you could pick one of those fixed points and rotate the diffeomorphism or do a little isotopy just near that point so that it's actually the identity. So I'm going to kind of pretend that we've done that. You might worry about how you've done that, but it, in the end, actually doesn't turn out to matter much. Okay, so maybe I make the point you could do this on any manifold as long as you had, you don't actually need to. If you have in a 4-manifold, two 2-spheres meeting transversely in a point, each of which has trivial normal bundle, you could do exactly the same thing. In other words, that's another way of saying that it's connected. Okay, so let me call that product of the two reflections. I'll call that capital R. So R for reflection. I gather Dave Auckly is going to come, but he calls that RR, which is it's fine because it reminds you that there's two reflections, but I don't know. It's too much to say. So if you're out there, Dave, sorry. Any case, since we've isotoped it to be the identity near a point, I can just glue that to the identity map on X. So back to my picture here. So on this portion, I'm doing the reflection. Nothing is happening here, and then I can put on this part, I can put the identity. Okay, so that's a description of a diffeomorphism on the manifold X connects on S2 cross S2. I could equally do the same thing. So that's what I call here Rx. I could equally do the same thing on using the other decomposition. I have a diffeomorphism that's sort of dependent on its origin with one. So the subtle point is that so what I claim, and I'll get to this in a minute, is that those diffeomorphisms actually, in the same sense as the spheres themselves, remember where they came from. They remember their roots as X or Y. So that's a much more subtle and I think interesting phenomenon than just looking at the submanifold itself, which is just you don't really need any new work. You just have to remember that you are allowed to do surgery, which is an older operation. There's an older construction. Actually, the original version of this was, as I say, from an old paper of mine from 1998, where instead of stabilizing by adding S2 cross S2, we stabilized by adding CP2, and then for sort of technical reasons, blow up a couple more times. If you like, you could think of just X blown up, the K3 surface blown up 3 times instead of once, as I did. But anyway, it's convenient to write it this way. And on this part, there's a bunch of diffeomorphisms, all built in some ways, instead of using the reflections, built out of complex conjugation, either on this part or on this part or some other. You can sort of decompose it in different ways and do something akin to complex conjugation. Complex conjugation, of course, for surfaces is orientation reversing, but for 4-dimensional, for real surfaces, anyway, curves, maybe we'll say, for its orientation reversing, but in dimension 4 it would be orientation preserving. So you can do a similar thing. And the theorem that I proved at the time was that if you did the sort of this reflection corresponding to X, or the reflection or this complex conjugation thing corresponding to X, that remembered the original Donaldson invariant of X or Y. And in fact, so the idea, which I sort of have given this variations on this talk enough times to realize that I can either give details about the construction or I can give details about detection. So this is a construction talk. But the idea, again, coming from way back when, was that I defined, in a way somewhat similar to what Donaldson had originally done, a sort of Donaldson type invariant. Instead of being going from, say, the set of 4 manifolds to the integers, this one goes from pi 0 of the diffeomorphism group, in other words, just from path components in the diffeomorphism group, using Yang-Mills gauge theory in style analogous to what Donaldson did. And it had satisfied these two properties. Well, first, I should, maybe 3, because there's something implicit here. Pi 0 of the diffeomorphism group, what does that mean? That's paths of diffeomorphisms. That's the same relation as isotopy of diffeomorphisms. It's actually a small, subtle point about the topology, that isotopy is supposed to be a smooth path, but this would actually be a continuous path, but you can always take a smooth path and turn it into continuous path and turn it into a smooth path. Yeah, the other way is easier, I guess. Yeah. Anyway, so the first property is just saying that this is well defined. The second is a calculation that says that for this particular diffeomorphism, which I didn't define, but anyway, there is a particular one that I have in mind. You get some multiple, a non-zero multiple of the Donaldson invariant of the manifold, and then a composition law. And so this would be true for any pair of diffeomorphisms. So in other words, that detects, albeit with this extra factor of 2, but still that's injective on the integers, which is a point, a non-trivial point here, detects something about pi 0 of the diffeomorphism group. You can do, by the way, a similar construction with the Seiberg-Witten equations. for technical reasons, for this particular diffeomorphism, it's only defined mod 2. And then you have this factor of 2, so it doesn't really do much good. And so I'll come back to that point, because this was something that was stuck on for a little while, and then we learned something from someone actually at MSRI, and which kind of got us unstuck. And so that, but in any case, a corollary of that is that if you take those particular diffeomorphisms, again, built out of these two different decompositions, so that this one manifold leads to two different diffeomorphisms, and the difference between those two diffeomorphisms, well, the composition of one with the inverse, that's actually well, first off, you can set it up so that that's topologically isotopic to the identity. So that's that goes trivially if you think about it not in a diffeomorphism group, but in pi0 homeomorphism group. That generates an infinite subgroup of this diffeomorphism of this kernel. So the phrase was is that homotopy does not, or actually the technical word in this setting would be pseudo-isotopy does not imply isotopy in dimension 4. So that's something different. That's a pseudo-isotopy not implying isotopy. Let me put it this way: in higher dimensions, and actually in dimension 3, no, sorry, not true. In higher dimensions, for simply connected closed manifolds, pseudo-isotopy, which is actually the relation that you see here, would imply isotopy. So that's a famous theorem of Cerf from whose name actually apparently is so that's Cerf. So maybe I should say this: Cerf for dimension, well, bigger than 5. There was some additions around 1960. Says that pseudo-isotopy, which is a slightly stronger relation, well, a stronger relation than homotopy, implies isotopy. Fundamental proof is true. So, so this is again a new phenomenon in dimension 4.
Greater than equal to greater than 5.
Yeah, well, that's what he proved, and then later people kind of came back and filled in. I think it's not true for 5. It's a little bit. I don't know. It's in French, and actually it's very beautiful. It's in French and it's hard, but it's a very beautiful. That's sometimes you hear reference to Cerf theory. Anyway, that's the origin of Cerf. This article is where Cerf theory was really laid out. I never met Cerf. I met his son, who told me his name is pronounced Ser. But they're perfectly happy to have it called Cerf because there's another Ser in the world. Anyway, so Dave and I, well, apparently starting in 1998, and with efforts to sort of fill in, there was a bunch of steps in this program. Some of which will show up in what I'm about to describe, found a bunch of similar results. Now, instead of having pi0, we studied the higher homotopy groups. And again, in higher dimensions, once people study higher homotopy groups or homology of diffeomorphism groups, and there's a huge amount known. It's a very complicated and technical subject, and not in French, but it might well be. Anyway, it's hard to figure out what the heck those guys are proving, and anybody's out there. It's just they're using very sophisticated mathematics to do that. So it's a little hard to know exactly how what we've done compares to what they've done. But in some qualitative sense, we get for assorted manifolds, not exactly the one that I showed you, we get large subgroups. Well, I shouldn't have said K. We can get large rank 3 billion subgroups, and sometimes even summands of those kernels. And but what we wanted was was actually to prove that those kernels are infinitely generated, because that's what it sort of looked like. And I won't go through the technicalities of why one theory is better or worse for this, but roughly speaking, if we could kind of take the results from the previous page and combine them with the recent results about these higher homotopy groups and do it with Seiberg-Witten invariance, then as it turns out, we had a method. We sort of had a method sort of sitting in our pocket for a couple of years to actually prove that all these groups are finitely generated, such kernels. Okay, so we were a little stuck on this point, and in fact, as you'll see, the construction, at least our construction, is a sort of inductive one. You sort of start with these results, sort of older results in this construction that I briefly outlined here. You sort of want to start with that, and then out of that, I'll show you how to, by a trick, to make the manifolds bigger, and then go from pi 0 to pi 1, make the manifolds bigger, go from pi 1 to pi 2, and so on. So we sort of had the inductive part all ready to roll, and what we needed was, as we teach our undergraduates, an induction is no good if you can't do the base case. So we needed a way to sort of do the base case in a way that was compatible with the inductive procedure. So we were sort of stuck at the bottom of this somehow. Dave is good at colorful terminology, so he called it the ladder. So we were stuck on the bottom rung. We had a ladder all built, but we couldn't figure out how to put our foot on the first rung. So maybe the 0th rung. Anyway, so we learned talking this fall with Hokuto Kono about something that was actually in a paper of his with David Auckly from a couple of years ago, which I'm sure I read, and so I don't know why it didn't stick with me better, but it didn't. Which was that in the Seiberg-Witten setting, if you weren't able to work a little harder, you could get a Z2 result, and then somehow, well, if you can prove something is non-zero mod 2, then, well, that means it's also not 0 as an integer. So that's a very common trick. So as it turned out, that the reflections that I was originally using, in other words, the ones built out of complex conjugation, well, those just like somehow had the wrong property for that. Those were always going to come out 0 mod 2. But in the paper with Auckly, Kono pointed out that these reflections built out of S2 cross S2, in other words, products of two things, those actually could be non-zero mod 2. So in fact, so in the same sense that there was a Donaldson invariant, where did that go? That was over here. There's a Seiberg-Witten invariant of certain diffeomorphisms, and as I say, it works better mod 2. It's for those reflections, it would actually be, you could do this mod 2. For the experts in the room, I think on this side of the room, this all has to do with the difference between mod 2 and not mod 2. It has to do with orientation. Well, anybody would guess that has something to do with some kind of orientation, but this has to do with whether these diffeomorphisms preserve or don't preserve orientations of some moduli. So somehow that's what's going on here. But in any case, we had these mod 2 invariants that are defined, and if you take a composition, that's again by the two reflections would preserve this homology orientation. In other words, preserve the orientation of the moduli space. This thing would be defined as an integer, and the composition law, as before, was a composition law. Well, that worked mod 2. So in other words, although this one, which maybe we wanted to use, is not defined over the integers, this sort of difference one is defined over the integers and can be calculated as the difference between these two things. So if you can sort of set it up so that, say, I think this one will turn out to be odd, would turn out to be odd, and this one turn out to be even, in fact, actually just sort of 0 on the nose, then you would get something of interest. So this is sort of how the pi 0 So this is, so the calculation then, analogous to the calculation I said before, really says that this reflection at least remembers something about the Seiberg-Witten invariant, and remembers its parent. So at this point, the actual x that I told you is probably not the right x to use, and I can't remember. I don't think I can do it on the fly to change it to some other x where the Seiberg-Witten invariant. So I think that one's okay. So I think that one was just fine. Never mind. Okay.
Can I ask a question
yes.
about just the pi zero result?
Yeah.
I mean, are there examples of things in that kernel that are not products of reflections?
Well, yeah, I guess. Yes. So maybe I should at this point point out that this sort of general method that I'm talking about, which sat there for a good 20 plus years with nobody paying much attention to it, much to my sorrow, and it's gotten very popular in the last 5 years. So there's a whole host of work by, I've already named Viralia, Kono, Taniguchi, and Krunhammer and Rufka famously showed that if you take a K3 surface, connect some another one, and do so you have this S3 or S3 cross I, you have kind of a Dane twist diffeomorphism. That's not isotopic to the identity, although it is pseudo-isotopic, topologically isotopic to the identity. Jamfeng and Lin took the same example, threw another S2 cross S2, that's still not isotopic to the identity. Especially the Krunhammer and Rufka one, there's no two spheres. There's no two spheres of self-intersection 0, at least that I know of in those examples. So I don't think those are not isotopic to the. So those are not sort of built by the same construction. They're detected by, in some sense, similar sorts of invariants. So there's lots of examples at this point. So yes, the answer is yes. There's plenty of examples this way, and there's now other ways of getting at say pi one of diffeomorphism groups. I should say, going back to the there was this corollary, by a variation of the original construction, I could show that this kernel was infinitely generated if you restrict it not to the diffeomorphism group, but to what one might call the Torelli group, the subgroup of diffeomorphisms acting as the identity on homology. So that one actually was in that case the kernel is infinitely generated. So that's sort of the source of the suspicion that that's infinitely generated, that this kernel ought to be infinitely generated. Or it was a natural question anyway. But so you can have finitely generated groups with infinitely generated subgroups. Right? Free groups have that property. So so although actually in the paper where I wrote this, for some reason in the abstract I claimed that this thing was infinitely generated. If you read the paper and actually the statement of the theorem, it says that I didn't have the wits to call it Torelli group, but I gave it some other name. But anyway, these days one would call it Torelli group. That pi zero in that case is infinitely generated. So there's lots of but essentially the same construction as I'm But yeah, to answer your question, to give us a succinct answer to your question, Chris, yes, there's lots of other constructions.
I was thinking more group theoretically, like when I said reflection, like is it possible that everything in that kernel is the product of order 2 elements in pi 0 bit? Or is that's probably too?
Yeah,
too much.
I have no idea.
Okay.
Yeah. Yeah, I mean it's a little tricky actually if you do. Well, this is getting a little into the woods, but there was this isotopy to make it the identity at a point. If you do it one way or the other way, the difference between those when you glue them together, that is exactly this gain twist. So what I've said. I mean, you just choose a convention and just do one thing, but that's actually it's not. I haven't actually told you exactly what to do. I mean, but the point is the calculation would work whether you sort of rotate it this way or rotate it that way. So I don't know any way to answer that question. That seems, yeah, the group theoretic structure of this is also something of a mystery. Okay, so I guess maybe the observation that just as I go forward, there are lots of different ways of getting four manifolds with different mod 2 Seiberg-Witten. So there's lots of, I mean, so I gave you a specific pair X and Y, but you could have done a lot of other things. Okay, so that's one thing. So let me now turn to sort of families of diffeomorphisms, families of other things, and maybe it'd be time to state a theorem. Well, I sort of alluded to this already. The diffeomorphism group, the homeomorphism group are topological groups. I think in high-dimensional topology, they treat the homeomorphism group as some kind of simplicial group or something like that. But for our purposes, it doesn't much matter. Anyway, let's just think of it as a group. I don't know, compact open or Whitney topology, and so therefore it has. So these are infinite dimensional things, but they have interesting homotopy groups. And again, it's a time-honored subject in high-dimensional topology to study them. So you have homotopy groups. I should have also said, similarly, there's homology groups. So there's various things you might imagine cooking up out of that. And the other one, which is quite natural from this point of view, and probably, I mean, all the results could have been stated in these terms already, was you could look at the classifying space for that group. So every topological group has a classifying space. In this case, what does it classify? Well, it classifies bundles over a given base space B with fiber Z and then diffeomorphism. No restriction on the structure group, so well, just diffeomorphisms, or if you did B homeomorphisms, that would allow homeomorphisms as transition functions. So those are three things whose topology are three aspects of the topology of those things. So here's sort of the theorem that we've now proved. I think we still don't know quite how to do this for pi 0, but in any case, so this is about the higher homotopy group. So this is a recent theorem of Dave and mine, really from the kind of observed in the fall. We're very slow at writing, so God knows when it will actually appear as a manuscript. So for any k, at least one, there's a simply connected four manifold, and there's lots of them. There's particular embeddings of the two-sphere or three-sphere, and all of these different groups have infinitely generated subgroups, and some of them actually you can prove that they're actually sum n, so we get some little extra information about the theoretic structure. Well, in all these cases, we're talking about the component. It's best to think about the component of the identity in the diffeomorphism group. The homotopy groups are all infinitely generated. The homology groups are all infinitely generated. The homology of the B-diff, the classifying space, those are all infinitely generated. And then you can also study the space of embeddings of a two-sphere, kind of the same, in some sense, the same two-sphere we were already looking at, or the space of embeddings of a three-sphere. And so, well, okay, so Dave's PhD student, Josh Ruberman, does this for spheres with other self-intersections. So here, actually, this is holdover from some previous set, from some previous setting. So he does this for other spheres, spheres of other self-intersections, and instead of looking at embeddings of the three-sphere, he looks at embeddings of lens spaces. So he gets some interesting results that way. By the way, yeah. Okay, so
Sorry.
Yeah, go ahead.
You're saying that in your result, the self-intersection of S2 and ZK is.
Yeah, these are all actually self-intersection 0 in this as I said. Sorry, this is a recycled slide from the previous one, which had to do with spheres of self-intersection, plus or minus 1. I can't remember. So, okay, so but these spheres happen to have self-intersection 0. But there's a trick that that Josh uses, that Dave and I have used in some previous work, that somehow if you know how to do things for one self-intersection, then you can kind of change the self-intersection and get similar results. So Josh takes advantage of that trick and does this.
So these Ks are the same for like pi k and then.
Oh yeah, so ZK is the one with pi k. There's some variations on this where, let's see, I don't think I write this down. You could actually take a ZK and know that all the homotopy groups pi k minus 2, pi k minus 4. So obviously the certain parity. You could get a bunch of different homotopy groups or a bunch of different topology groups, all to be non-zero. So there's a little. It's kind of it's just a sort of a trick. So you get it. So in other words, you get these very big kernels in all sorts of dimensions, and it's just as this sort of an artifact of the trick. They all happen to lie in the same parity. Probably that's, as I say, that's an artifact we just haven't done this. So. Okay, so let me So last bit of commentary on this before I spend a couple minutes at least on the construction. So first up, in each case, if you pass to the corresponding thing about homeomorphisms or topological embeddings, everything becomes trivial. At least for pi k of things. Sorry, this is supposed to say pi k. These, or maybe hk. Not the d-diff ones. Then those subgroups are actually summand. So some little popular thing these days in topology to say, oh well, no, I didn't just get a subgroup, I got a summand. So that's because they're coming from some kind of subjective homomorphism to a big infinitely generated 3 billion group. And then there's this sort of innocent property which goes back to what I was saying about Wall's result and the sort of concrete instances, which is that in each case, well, if you're careful about it, there's a kind of a well-defined stabilization result. So you just take the families, you can kind of assume that nothing interesting is going on a disk, and then you add on, you don't do anything. You add on another S2 cross S2, and the whole thing just falls apart. So those things are all trivial in that sense. So that's true for manifolds, and one of the missing steps, which was to prove that for the again, sort of starting this, getting on the first rung of the ladder, was to prove that when you, so remember what this is. Well, sorry, let me just establish some notation. So I had these two manifolds, X and Y, and by the Mandelbaum and Moishazan result, those have the property that if you add S2 cross S2 to both sides, you get the same thing. So there's, so let me call this common manifold I think, sorry, this manifold, that's, oh, right, yeah, this manifold, right. So so the common manifold, I called Z before, but I'm going to start this inductive procedure. So that's the 0th stage. So I'm just going to call that Z0, so I can keep track of it. And then I'm going to make a Z1 and so on. So that's the first one. So that you could say something in that here. So so Dave and I had in mind, apparently since 1998, the idea that if you could prove that the diffeomorphisms you got from the original trick stably, if you just added S2 cross S2 to those, or the identity on S2 cross S2, then that would give you some kind of isotopy, and then maybe you could use that isotopy to create interesting elements in pi1 of diffeomorphisms of the stabilized map. So that's roughly speaking what we wanted to do. So the first step of that was from a little while ago. So Dave and I and Hee-Jung Kim and Paul Melvin showed that, in fact, if you take that Z0 and you stabilize it once, then the two spheres that are really at the base of the construction, these remember there was the SX and the SY, those two things become smoothly isotopic. Okay, so that was, so in the end, the proof of that's not hard, but like lots of things, it takes a long time to figure out how to do it. And but as a consequence of that, well, this is true for the A spheres, and sorry, this is supposed to be A, and then the B spheres are also there was the other sphere; those are also smoothly isotopic, and it follows from that that the diffeomorphisms, if you sorry, I just wrote something. So if I take this thing and then add on the identity on S2 cross S2 is isotopic to the other. So these two were different, this one and this one. If I added on the identity on S2 cross S2, so the sphere, so you add an S2 cross S2, the other spheres that used to be different are now the same, and so the diffeomorphisms are the same. Okay, so that's just a geometric construction. You can actually draw pictures of it, and that was a major holdup, was figuring out how to draw a good picture of that. Okay, so alpha. So let me just again introduce some new notation. So alpha 0 is the original diffeomorphism, which was shown to be of infinite order using this idea of Kono. So and okay, so the question is how to leverage this this stable isotopy to get an element of pi1. So if you're showing that two things, so you have these two different things, put them in another manifold, and now they're isotopic. So that gives me a path from one thing to another, but that's not a loop, right? It's sort of an interesting path, but the question is then how to turn that path into a loop. In other words, like so if there was sort of some other way to join up the ends. Anyway, well, here's what we came up with. So we do this by making this manifold bigger. Okay, so I'm going to form a new manifold called Z1, and as you can guess, this is the this is the inductive step, and we just keep doing this. So this is what's called fiber sum, or submanifold sum, I think is a more accurate way. So the Z0, remember that was built out of a K3 surface. K3 surface is an elliptic surface, so it's almost fibered over the two sphere where the fibers are tori, and the other one that sort of also has lots of tori of self-intersection 0. So you can remove a neighborhood of each torus and then glue the things together. Kind of like connected sum, which would be like submanifold sum along 2 points, but here we're doing it along tori. So this is a very useful operation in four-manifold theory, and it actually sort of comes from algebraic geometry and symplectic geometry. So we take two of those and add them together. And one point, so Z0, remember that had an S2 cross S2 summand, and one small, important point is that sum, that those tori stay far away from the S2 cross S2s. Okay, so those are just sort of, the S2 cross S2s are off in a corner. In fact, here's a schematic picture. So this is supposed to be Z0. This is its torus. This is its torus. This is the S2 cross S2 sort of sitting there. Here's another copy. It looks just the same. And now we do this sum, and it's got two S2 cross S2 summands, and the torus is sort of over here. Okay, so there's sort of two copies of S2 cross S2 in this Z1. There's this one on the left, and there's this one on the right. Okay, I did write that. Okay. Well, anyway, now it says it. So it must be correct. Okay. So so let's look at the the copies of those spheres on the left. Okay. So those things. Well, I've got an S2 cross S2 summand, so those spheres are now isotopic. The red one, maybe it's the D spheres. The blue one is the A sphere. So those things are isotopic. So so that means if I sort of do this diffeomorphism on the left part, the interesting diffeomorphism, and I connect some along this, and I just sort of add the identity on this part, that's isotopic to the identity on Z. And so it's it's a slightly more complicated manifold, but not too bad. And so maybe F is the name of the isotopy. So anyway, so it's a little hard to explain all this, but this is a fun verification. If you have a couple of diffeomorphisms, well, we're in some kind of group, so we can multiply them just by composition, and we can take commutators. So if we take the commutator of this isotopy with this single diffeomorphism, but now it's sort of the same diffeomorphism, except for now on the left we're doing the identity, and on the right we're doing this alpha 0. So what's the point of that? Well, the identity, of course, commutes with everything. So sort of at the endpoints, you're getting the identity, and basically this has the effect of turning that interesting path. Now at the endpoints agrees, and it gets turned into a loop. Okay, so you just have to sort of sit down and just work out like what is this at time t, and at time 0 and time 1, you're getting either things that where one's the identity, so they commute, or you're getting two things that are the same, and therefore they commute. Anyway, so there's some little trick like that. And
so where is it important that you're doing a factor sum along the torus?
So the main point about all that is that when you sort of yeah, that's a good point. Well, somewhere in all that, we have to calculate an invariant, and somewhere in there we have to use the calculation of the Seiberg-Witten invariant for some four manifold, and that four manifold will be a fiber sum of two other four manifolds. That's that's sort of the best. And then there's a formula for how things behave under fiber sum. So you could do this with various other constructions, as long as it's sort of there's the kind of constructions that preserve non-triviality of Seiberg-Witten. So that's sort of buried in there. Okay, so that's the idea then works in general. So because it's built out of this F0, and because we have this part over here, if you add another S2 cross S2, that element in pi 1 becomes trivial. So it's got a contraction, and then we can do the same thing. And then, again, by summing on this extra summand, and each time what you find, just using a similar commutator formula, you get you can build yourself a series of things. And so the last point, well, is sort of summarized on this slide. So in this way, we build a series of elements. Alpha naught was the original one. Alpha 1 was the one I sort of just constructed. Alpha 2 is coming from the second stabilization, and so on. And the main point is that that this operation actually preserves, well, up to sign, because we're a little unclear about orientations. It preserves the Seiberg-Witten invariant. So there's a Seiberg-Witten invariant, which I'm sorry, I'm not going to have time to describe, that applies to, say, families of diffeomorphisms. And so the higher dimensional one, so for the K parameter invariant, is equal to this commutator thing is equal to the K-1 parameter family invariant for one of the ingredients. So that's some kind of gluing formula. And the point is so what is this? So in summary, what does this much of the construction show? That would show that each of these groups for these particular ZKs is got is infinite. In other words, contains a z. Well, how do you find this for do this for the infinitely generated? Well, you just use lots of different manifolds as you use manifolds that have lots of different Seiberg-Witten variants for different spin C structures, and you just have to kind of anyway. So there's some at that point it's just sort of technique, and that part's so this is the heart of it is right here. So anyway, maybe maybe I'll just leave that slide up there, and so this is supposed to, this slide somewhere in there is telling you how to actually cook up invariants, and then the point is that they satisfy this inductive property, which is really some kind of, that's the analytic heart of, well, so there's two, so what's hard in all this? One is this coming up with this commutator idea to sort of boost things up, and then the second part, where sort of most of the analytical work is improving this, this sort of stabilization or connected sum theorem. Anyway, so let me stop that.
Questions today?
So again, quick enough.
Well, how honestly am I supposed to answer that question? I turned the Zoom off. The initial result that I alluded to with Dave and I is almost completely written. That's the Donaldson version, and it's just checking a lot of details in some in its gluing formula that analogous to the one at the bottom. So that one is being written up, and I don't know. I just kicked it back to Dave a few weeks ago, and so he's supposed to be doing his final revision. So that's supposed to be the other one. We'll write, when we're done with the first, we'll write this one. So it's being thought about and discussed, but it's not. But we haven't actually put pen to paper. So is that an honest enough answer? Okay.
If you remove simply connected from your hypotheses, does this solution all much easier?
Easier.
Or I don't know. I mean, what happens when you remove simply connected?
Yeah, that's an interesting question. Actually, I posed to one of my, well, I guess probably my last remaining PhD student, the question of what happens if you just add on something simple like S1 cross S3 to these things stay isotropic. And it seems likely that will work. In other words, at least the pi0 version of this will work. And higher pi k things seem a little bit tricky, but I think they, I think it should that should work. In other words, the detection results all will work. If you add on, if you change the fund, it would work as stated if the first homology is 0. I don't think there's any change required. I don't know any good examples of that. Maybe even if the first homology, it's just torsion. Probably that all just works as stated. I don't know any. Do you have any example in mind that you're thinking of?
Not really.
But once you start adding, you have consider either Donaldson or Seiberg-Witten invariants when B1 is non-zero. You have to get the invariants you're using are slightly more elaborate, and then not entirely sure. And so defining those invariants actually gets there's some subtle points to that. I could explain it. We'd have to kind of go through all the some of what's up on the screen. It's a little bit tricky to think that one through. But yeah, I think that should all work, and it's a little easier. And it's definitely tricky in the Donaldson case. I don't actually know how to do it. D1 is non-zero. And it's definitely, I think those technical issues should be easier to deal with in this algorithm. So that's what I suggest.
Is there a sense, I guess the example like of the K3 is perhaps the simplest example where you see some of these phenomena?
Well, actually, I think these days, so this recent work by, again, it's from the point of view, this page somewhat similar, and work by Kono and Jianfeng Lin, where they show. So one of the things that you learn in higher dimensions is that diffeomorphism groups satisfy a version of what's called homology stability, which has to do with the way that things behave when you add. If you are in even dimensions, it's easier to understand. You have maybe a simply connected manifold of dimension 2n, and you add lots of copies of Sn cross Sn, then the homology of the diffeomorphism group tends to stabilize in some various ways. And they proved that that's not true in dimension 4, and that it's the manifolds, at least the initial manifolds that you're using, can be simpler. As far as I can tell, I don't know if it's any 4 manifold, but anyway, those manifolds can be simpler. So there are some results using, let's say, just related sorts of techniques that get where you get meaningful information about the homology, in this case, of social groups. So that's interesting. It's also, one of the things one of the reasons that we do the construction this way is because so you can get interesting things about diffeomorphism groups and their homology or their homotopy groups for other kinds of manifolds. But one of the key points for us to try to do is to show in every case that those things are sort of trivial once you pass the topological category. So it's not all that clear what happens for some of these results of the topological category. And the reason for that is that there are these wonderful results of Quinn and Perron that tell you when diffeomorphisms or actually homeomorphisms are topologically isotopic, but no one is able to do there's no criterion for when a loop of homeomorphisms is trivial. There's no, that's a hard problem. Maybe pi 1 of homeomorphisms is doable, but pi 2 is going to be just like this, just too many things that break down topological. So one of the reasons that our manifolds are big is that we want to kind of preserve this stabilization property, and the benefit of our inductive construction is that making all of the topological things trivial is really coming out of the result from pi 0. And that's somehow because, when you do a commutator and just like one thing is trivial, then that trivializes everything. So it's kind of that, it's a stupid trick, but it's fully like it.
Stupid works.
Yeah, lots of times.
Yeah, it works. It's so stupid.
Yeah.
Any other questions? Thank Danny again.